Welcome to Module 6, Port-Ship Interface. The aim of this module is to deal with ship-port interface and explain how ship in-port operations can influence the ship energy efficiency and port air quality. The module includes all aspects of ship operations in ports and relevant technologies, fuels, as well as operational measures for reducing the ship in-port fuel consumption and air pollutants. Upon completion of this session, you will explain the main activities of the port and the port's significance in the maritime industry. Recognize the importance of ship port time in the energy-efficient shop operation context. Describe the way that a ship's just-in-time operation in a port may be realized. Identify factors in portside management that affect efficient ship operations. Explain why onshore power supply can reduce the ship's port-related pollutions. Discuss the requirements at portside and shipside for OPS and the barriers to its implementation. Be able to analyze the impact of OPS on ship at berth air emissions and energy efficiency. Become familiar with port-related green initiatives and port environmental programs, and be able to name and give a brief explanation of other green port-specific initiatives. A number of topics are covered, including 1. Introduction to ports and port area greenhouse gas emissions. 2. Ship time in port and just-in-time operations. 3. Technologies for port air quality and greenhouse gas emission reduction. 4. Ship in-port energy efficiency operational measures. 5. Onshore power supply. And 6. Green port initiatives. Port management and activities. Port management is a complex process. There are a number of chains in this process. Normally, these chains are made up of a variety of links. Often, different parts of the chain are controlled or managed by different players, but some activities are also integrated across the links. So, ports could have a relatively complex management and decision-making structure. No two ports are physically and economically the same. Therefore, their operations will depend on the port as a physical entity, taking into account the various activities, such as facilitating the loading and unloading of vessels, freight handling and storage, and access to land-based transportation. Clearly, these are quite diverse activities which combine to make port services diverse and complex. There are also added value services. These can include a variety of marine services such as bunkering and repair and real estate activities in ports. The large number of parties involved in port activities, each pursuing their own objectives, leads to a considerable diversity both within ports and between ports. Therefore, a generalized comparison between ports may not be fully possible. Moreover, the situation is further complicated by the fact that different ports often work under different economic, legal, social, and tax regimes because they are regarded as part of national entities in each country. Thus, ports are to a large extent different from each other. Port management varies from port to port, from country to country. Shipping companies and ports rely on many players. These include the port itself, pilots, towage services, ship repairers and provisioning, waste reception facilities, and bunkering companies. Some of the port air emission sources are as follows: cargo loading and unloading processes or devices, trucks and other land-based transportation units, buildings and building facilities, harbour crafts and vessels, and ships calling at ports. The emission sources directly associated with ship operations in port include those due to propulsion engines, auxiliary engines, and auxiliary boilers. Additionally, there is volatile organic compound that is associated with bulk liquid cargoes and various ozone-depleting substances that are due to refrigeration systems. From an air pollutant perspective, vessels can produce a significant amount of the following: nitrogen oxides, particulate matters, sulfur oxides, volatile organic compounds at some ports, some carbon monoxide and unburnt hydrocarbons, black carbon or soot. Depending on geographical configuration of the port area and the type of vessel, these combustion systems can have varied levels of emissions. It is important to know for the vessel in question which of these plays a more important role in ports when it comes to emissions and energy efficiency reduction measures. Most emissions from ships in port are the result of diesel engines burning heavy fuel oil. Compared with land-based transport, the marine engines are not as strictly regulated as their land-based counterparts. National and regional regulatory authorities have limited control over international ships, other than on their own flagships and to some extent ships visiting their ports. Reducing emissions from shipboard diesel engines is therefore one of the significant challenges and opportunities related to improving air quality in port areas. The unique challenge associated with the port area with regard to reducing ship emissions is how the emission sources listed above are associated with various modes of ship operation in the port area. Generally, a ship in port area has two general modes of operation. Based on discussion about ship-related and non-ship-related emissions in port, emissions in port areas can be dealt with by measures to be implemented at ship level and port level through analysis of the following: non-ship-related air emissions and ship-related air emissions. The ship-related emissions at port, as indicated above, can be divided into those related to ship maneuvering and transit in the port area, and those when a ship is at berth. To reduce them, a number of main measures can be followed. 1. Just-in-time operations of ships. 2. Ships' cleaner fuels. 3. Ships' emissions abatement technologies. 4. Shipboard energy efficiency when in port. 5. The use of onshore power supply, known as cold ironing. These measures will be discussed at length in the next few slides. The main shipboard systems working when a ship is at anchor or at berth include auxiliary machinery and equipment, diesel generators, boilers. Additionally, and on some ships, cargo handling equipment may be in operation that would provide extra opportunities and further measures for energy saving. However, in this section, only 3 items stated above are investigated. The ship's diesel generators operate in port in order to produce electricity for the operation of a large number of machinery and systems in the engine room, deck, and accommodation areas. Among them are the engine room auxiliary machinery like fans, pumps, and other devices. On the accommodation side, the need for lighting, HVAC, heating, ventilation, and air conditioning, and galleys exists in port. In order to save energy and reduce emissions, auxiliary machinery utilization in port should be minimized, with consideration for safety. There's practical evidence that such machinery is normally overutilized in ports. Ship staff may follow the same processes as when seagoing and keep the machinery running in the same way as during seagoing conditions. This could also be considered as a way of avoiding additional processes and remaining ready to leave the port without the need to restart some of the machinery. It may be also because the company may not have plans and procedures on how the port operations with regard to machinery utilization need to be handled. This should not be the case, and it can be changed by specific planning for the engine room machinery operations for at berth or at anchor operation to ensure energy efficiency while safety is taken into account. The main aim of the plan will be to save energy through switching off the unnecessary machinery. As examples, the following may be undertaken. Minimize the number of aircon units operated or switch them off when conditions permit. The number of engine room ventilation fans should be reduced in port or adjusted to slower speed. Minimize the use of compressed air and its use where required. Minimize lighting loads. There are a large number of pumps on board, such as seawater cooling, steering, engine water circulating, and lubricating oil pumps. These measures will reduce the need for auxiliary power and the number of auxiliary engines running. Boilers form a major part of shipboard energy consumption in ports, in particular for certain types of ships, such as oil tankers. Although boilers emit less harmful emissions than diesel engines, for example, less nitrogen oxides, nevertheless, the control of their energy use will be beneficial for the port area emissions. This is because, as the ship auxiliary boilers mostly operate at low loads while at port. At low loads, the energy efficiency reduces and emissions factors increase, which is not helpful. The use of parallel operation of two boilers should be avoided. This not only improves the energy efficiency of the working boiler, but also gets rid of electrical requirements for the second auxiliary boiler. Planning and optimization of cargo discharge operation is another area if it relies on steam-driven cargo pumps, for example in larger oil tankers. In some of the ships, there may be provisions for a mix of electric and steam-driven pumps. Proper planning could be done to avoid excessive use of boilers. Plan and optimize ballast operation if it relies on steam-driven ballast pumps. In many ships, the ballast pumps are now electricity-driven, or a mix of steam and electric drives are used for this purpose. In some ships, such as oil tankers, auxiliary boilers may be used for inert gas generation or IGG. The whole process of generating inert gas and its use can be part of optimization. As for inert gas generation, the boiler would normally run at a very low load. Normally a dedicated IGG system is used to avoid use of the large boilers. International shipping is the most energy efficient mode of cargo transport in world trade. But unfortunately, it is also a major producer of nitrogen oxides, sulfur oxides, and carbon monoxide emissions. When it comes to ports, there have been limited studies on port operation management and its potential contribution to ship energy efficiency. The main reason for this may be the lack of international maritime organizations' regulatory authorities on ports, because the IMO's main focus is on ships and international shipping rather than on ports that are mainly regarded as national entities. In spite of this lack of regulatory focus, marine ports are important for shipping energy efficiency, and in particular, they play a major role in delivering an energy-efficient ship operation. Therefore, their roles and responsibilities and what they could do need to be understood. There are a few effective ways of reducing ships' fuel consumption. Two main examples are operating the ship at reduced speed during passage by just-in-time operation. Trim optimization and ballast water management can contribute to significant energy saving. Port operation has impacts on both of the above. For example, when it comes to the energy-efficient ship operation, reduced ship speed at sea is closely related to the minimization of a ship's time in port. A ship's time in port will be referred to here as ship's port time. Reduction in port time through high-quality port operations allows shipping lines to improve the operational efficiency through reduced ship speed and therefore fuel consumption. This calls for examination of all aspects of port operation in order to find practical ways to cut down on ship port time. One possible way is to make a ship to operate just in time that involves getting rid of the waiting time in port. This will not only help shipping lines to get the maximum notice of berth availability, but will also facilitate the use of optimum ship speed at sea. Furthermore, reduction of berth time by improved cargo handling could be another way to reduce ship time in port. However, few studies have yet been done to identify the relationship between ship time in port and efficient ship operation at sea. In the case of import cargoes, the latter consists of activities that are cargo handling in the apron area, transfer to storage, yard storage, and gate processing. This diagram is representative of a container ship terminal. However, similar diagrams could be constructed for other ship types to define the activities in port operations. When a ship arrives at the entrance buoy of a port, the pilot comes aboard the ship to help the master in maneuvers to the designated place. If no berth is available on arrival, the ship is assigned an anchorage area. If the berth is available, the ship is berthed with the help of tugs, depending on ship size and port rules and regulations. At this point, line handling services are provided at the berth. In particular, the time when a first line is connected to the pier or dock is very important, since it is the starting point of the so-called berthing time. The berthing time stops when the last line from the ship lets go of the bollard as it leaves the berth. When berthed, the customs, immigration, and quarantine authorities may board the ship. Usually, cargo handling is not made until the authorities have completed their inspections, with the exception of the container shipping business. In dedicated container terminals, container boxes are unloaded and loaded, usually using a gantry crane at the apron, where containers are moved to and from storage by in-terminal movement vehicles. Once the container cargoes are unloaded, they are transferred to an assigned slot. This is the space in the yard where storage operations occur. The containers are stored until they are inspected and claimed by the consignee or importers. The containers are then moved from the yard onto trucks or rail cars for their final destination through the gate operation. Gate processing includes weighing the container, reviewing paperwork, and conducting a security check. All the above steps are shown in the diagram on the slide. Tough competition in the last couple of decades has caused container shipping in particular to be able to achieve profit only through economies of scale. This has led to larger ships and ever shorter cargo handling times and demurrage. Today, new potential for economization can only be achieved by reducing operating and fuel costs. Two ways out of this predicament are either to use slow steaming, meaning a ship's speed is reduced to save fuel, or to deploy even bigger ships, allowing the higher fuel cost to be spread over the additional tonnage. However, increasingly strict environmental requirements in harbours and en routes limits the engine size and thus the size of the ships. When it comes to the operation of container shipping lines, the timetables of the routes are normally fixed. If the ships are delayed in port at some points, they are forced to make up for the lost time by increasing their speeds at sea. As illustrated by the diagram, a ship's voyage time is composed of time at sea and time in port. The search for efficiency across the entire transport chain means that responsibility for what can be delivered does not reside with the owner-operator alone. A list of all the possible stakeholders in the efficiency of a single voyage is long. Obvious parties are designers, shipyards, and engine manufacturers for the characteristics of the ship. Then there are operators, charterers, ports, and vessel traffic management services for the specific voyage. All the involved parties should consider the inclusion of efficiency measures in their operations, both individually and collectively. When it comes to efficient port operation that aim to reduce the ship's time in port, as discussed and shown in the previous slide, waiting time and berthing time are two key components to consider in more detail. If the ship involved gets a berth on arrival, there will be no waiting time. In this regard, just-in-time arrival and departure is very important for shipping lines to operate their fleet efficiently. According to the 2012 guidelines for the development of a ship energy efficiency management plan, good early communication with the next port of call should be an aim. This is in order to give maximum notice of berth availability and facilitate the use of optimum speed where port operational procedures support this approach. Optimized port operation could involve a change in procedures that are followed in different handling arrangements in ports. Port authorities should be encouraged to maximize efficiency and minimize delay. Regarding the just-in-time arrival or departure of ships, from the viewpoint of ship operators, the reliability of the berthing window is another issue to be looked at. In other words, on-arrival services for ships have to be guaranteed between port authorities and shipping lines. Otherwise, even though ships are already in port, they might have to wait until berths are available. This will definitely make the time at sea shorter than anticipated, thus increase ship speed in passage, which will be used to counteract the lost time. This will be counterproductive in terms of efficiency of total voyage time or fuel consumption. In this sense, the relationship between ship operators and ports must be kept close and the operations harmonized in order to enhance reliability for securing on-arrival services in port. Having a contract for a dedicated terminal with shipping companies on a long-term basis is an exemplary case of resolving this kind of reliability issue. Responsibility for efficiency across the entire transport chain does not only reside with the owner-operator. There are numerous stakeholders involved. Obvious parties include designers, shipyards, and engine manufacturers who are responsible for the characteristics of the ship, operators, charterers, ports, and vessel traffic management for the specific voyage. All the parties involved need to consider the inclusion of efficiency measures in their operations, both individually and collectively. When it comes to efficient port operations that aim to reduce the ship's time in port, waiting time and berthing time are key components that require detailed attention. If the ship involved requires a berth on arrival, there will be no waiting time. In this regard, Just-in-time arrival and departure is very important for shipping lines to operate their fleet efficiently. According to 2012 guidelines for the development of a Ship Energy Efficiency Management Plan, or SEEMP, good early communication with the next port of call should be an aim. This procedure allows for maximum notice of berth availability and facilitates the use of optimum speed where port operational procedures support this approach. Optimized port operation may involve changes in procedures depending on different handling arrangements in particular ports. Port authorities should be encouraged to maximize efficiency and minimize delay. The diagram shows the actual operation times for a specific ship, denoting that 23.3% of her time is spent in ports, combining berth and anchorage. The same ship was analyzed for a number of port calls and just-in-time operations, and the required time for just-in-time operation was estimated. If operated according to port just-in-time, the ship time in port will reduce from 23.3% to 16%, a reduction of about 30% of port time. For calculation purposes, it is assumed that the ship would, in practice, get partial just-in-time operation, and thus port times could be reduced from 23.3% to 20.3% in a real feasible scenario. It is further assumed that the extra time gained from better port operation will be used in passage, thereby increasing the in-passage periods from 75.2% to 78.2%. This extra time will then be used to proportionally reduce the in-passage ship speed, assuming that the total annual number of port calls remain the same. The reduced ship speed is then converted to fuel consumption reduction, using the well-known cubic relationship between ship speed and required propulsion power. CO2 emission reduction is estimated using fuel consumption reduction and relevant emissions factors. The table shows the result of a simple calculation in terms of a ship's fuel consumption reduction, denoting a reduction of more than 1,000 tons of fuel consumption per year. This exercise shows how effective the reduction in port times could be on the overall energy efficiency of a ship, and how large gains could be achieved through better port-related operations. Each port or terminal has its own port management system for the efficient and effective operation of the port, which we refer to as Maritime and Port Operation System, or MPOS, in the example to be explained here. This is a customized management tool that focuses and optimizes the work of agents, entities, and port services on ships by coordinating the actions, controlling them, and allowing them to analyze how best to reduce the cost and time. All the parties concerned, including the ships, must participate in the MPOS from prior to the ship's arrival in the port to the time of the ship's departure from the port. Whenever the ship wishes to enter a port, the request for berth is made through communications services, normally internet, well before arrival, and is confirmed by the MPOS against International Ship and Port Facility Security, or ISPS, and the Dangerous Goods Codes before issuing the preliminary authorization for berthing. After issuing the preliminary berthing authorization, the MPOS compares it with information from the anchoring area and with activities of any anchored or berthed ships, nautical activities inside the harbour, status of maritime signals, maintenance status of berths, and then informs the berthing operation to the ship and the pilot service. The MPOS supervises at all times that there is compliance with the operating procedures. The MPOS informs and coordinates all port services regarding berthing maneuvers, also informing the other agents. Furthermore, throughout this phase, The MPOS is capable of performing the control actions and coordination tasks with other agents, as shown as the diagram in the slide. Generally, the MPOS controls port activities relating to maritime safety and the protection of the marine environment. Typically, the MPOS is part of the Port Authority organization and is responsible for ensuring the efficient flow of traffic through port and coastal waters, including allocation of vessels to berths, and on behalf of the government or Port Authority for coordinating all marine services. Major port services that are related to MPOS are as follows. Pilotage services. These are services given by maritime pilots that provide an essential and unique service to the shipping industry. Their principal role is to provide critical independent local knowledge and navigational information to vessels, and to bring the highest level of ship handling skills to maneuver vessels within their port. The prime obligation of pilots is to provide a critical public safety service by ensuring the careful management and free flow of all traffic within their pilotage area, thus protecting the environment. Towage services. These are services provided by a small, strongly built, powerful tugboat that is used to guide large ships into and out of port, and to tow barges, dredging and salvage equipment, as well as disabled vessels. Tugboat operations are typically carried out by private firms. If the volume of vessel traffic is not sufficient to support a tugboat service on a commercial basis, a port authority may be obliged to provide such a service itself. Line handling services by line boats. These are the services given by line boats that help the ship to be berthed. When berthing, once the lines from the ship are given to line boats, they approach a berth and try to throw a line to someone on land who ties off the lines at the dock. Mooring services. These are the services that secure a ship to the designated place, that is a berth or dock or buoy or anchoring with 2 anchors. Mooring services in smaller ports can be provided by the local stevedore. In larger ports, a mooring service is usually performed by a specialized private firm. Especially in complicated nautical situations, for example, single-point mooring buoys, specialized piers for chemicals or gases, or ports with large tidal differences, mooring activities require expert skills and equipment. A port authority may choose to regulate this activity when only one specialized firm exists. Vessel Traffic Services, or VTS, and aids to navigation. This is a marine traffic monitoring system established by port authorities. VTS is a service designed to improve vessel traffic safety and efficiency and to protect the environment. It offers the potential to respond appropriately to traffic situations that emerge in an area. VTS is usually part of a port or a maritime authority. Such services are provided in port areas and in densely used maritime straits or along a national coastline. VTS should be regulated by the competent authority. Responsibility for aids to navigation usually rests with the National Maritime Authority in port approaches and in coastal areas, and with the Port Authority in port areas. Often, provision and maintenance of buoys and beacons are contracted out. Because aids to navigation are generally part of an integrated maritime infrastructure, the costs of providing these services are included in the general port dues. As the above list of services shows, ships may use the above services in addition to cargo handling services. This then may have impacts on port time of the ships. Cargo handling is, in most cases, under the control of the port. Optimum solutions that are matched to the ship and the port requirements should be explored. Whatever solutions are considered should contribute to increasing the gross berth productivity, which means faster cargo handling that can lead to reduced berthing time. For example, when it comes to container terminal optimization, the integrated planning and scheduling of all the activities of a terminal can be suggested to increase moves per hour and reduce costs. To improve cargo handling, the following planning needs to be improved. Berth planning, cargo handling equipment scheduling, all different types of cranes. Efficient cargo handling in port can definitely be helpful for the environment. A well-planned cargo operation, both in port and on board, can reduce the level of emissions from the ship's machinery that leads to reduced energy consumption per transported unit. Ways to improve cargo handling resulting in environmental benefits include the use of an internal movement vehicle that has less fuel consumption per cargo unit, the introduction of high-capacity loading and unloading operations with lower emissions to reduce the ship's time in port, safer and easier cargo operations and monitoring, the application of new technology with advanced software tools, the use of eco-friendly and user-friendly cargo handling products, well-trained shore staff and ship staff who are keen on safety and environmental matters. Cargo handling, upgrade of cargo equipment. This could improve the time of cargo loading and unloading. Upgrade of cargo handling equipment can lead to less time in port. Energy efficiency of cargo equipment is also important and will depend on their source of power. The use of eco-friendly and user-friendly cargo handling products. Well-trained shore staff and ship staff who are keen on safety and environmental matters. Port operations involve not only ship operation but a lot of other activities. These include cargo loading and unloading, ground-level port-related transportation and activities of harbour crafts for provision of various services to ports or ships, such as dredging, tugs and bunkering. The prime mover for most of these vessels, vehicles and cargo handling equipment is diesel engines, although a move to electrification and use of other technologies is underway. In this section, technological solutions for port area emissions reductions and GHG emissions reductions are discussed. A number of studies have been carried out in the past. The most prominent ones are those by the International Council for Clean Transportation, or ICCT, and the IMO. These studies are used as the basis of material in this section, and the main outcomes of these studies are highlighted. Most of the studies performed on port-related emissions concentrate on port air quality. One of these is reported by the ICCT in December 2012. In this report, the ICCT highlights the technologies that could be used in diesel engines as the prime mover for ships and portside trucks. The main focus is on pollutants, including particulate matters, carbon monoxide, sulfur oxide, nitrogen oxide, and volatile organic compounds, or VOC. The type of technology identified for reduction of emissions are diesel oxidation catalysts. This is a device installed at the back of the engine on the exhaust gases passed to oxidize such pollutants as CO, PM, and HC. Diesel particulate filter. This is the device used at the back of diesel engines on the exhaust gases path to trap the particulates and prevent them from leaving the engines. The SCR, or selective catalytic reduction. This is a very well-known technology for significant reduction of NOx emissions. As the name implies, it works by use of agents at the presence of a catalyst to convert NOx to N2 and O2. Exhaust gas scrubbers. Again, this is a very well-known technology for the back of engines on the exhaust gases path to capture the SOx and prevent them from leaving the engine exhaust. Exhaust gas recirculation. This is a well-known technology that aims to reduce the engine's combustion temperature and thus reduce NOx by circulating part of the exhaust gas back into the cylinder. The table summarizes various options, itemizes potential applications for use at ports, provides estimates for the reduction potential for various pollutants, and provides basic cost estimations for each option. These options show significant potential for alleviating air quality issues from ports, but are mostly considered as options for COT reduction. In fact, most of these options may lead to a small increase in overall fuel consumption, as for example, nitrogen oxide or NOx control methods most of the time make engines less efficient. The MEPC 68 INF.16 presents the results from the above technical and operational measures identified and studied. The following key findings that are relevant to this section are reported by the MEPC 68/INF.16 report. There are numerous technical measures that are available for ship-port emissions reduction and energy efficiency. Experience with some of these measures is over 10 years old. The technical measures are quite extensive. They include engines, boilers, after-treatment technologies, fuel options, alternative power systems, and operational efficiencies. There are no one-size-fits-all technical measures for ships and ports. Case-by-case studies are needed due to numerous variables. These variables are pollutants targeted, port configuration, cargoes handled, drivers, barriers, and ships calling at the port, vessels servicing the port area, vessel configurations, operational conditions, and the nature of technical measures. When the ship arrives at a port, there is some limited scope for the ship to reduce its fuel consumption while at anchor or at berth. While such reduction in fuel consumption may not have a significant impact on a ship's overall annual fuel consumption, the impact on port air quality could be significant. The main question is, can shipboard staff do anything to support a more efficient ship and port operation? A number of measures can be identified that, if implemented, would reduce fuel consumption for the benefit of a ship's energy efficiency and port air quality. These measures assume that a ship will not be connected to shore power, or a major switch in terms of fuel type will not take place, as these kind of changes may make some of the arguments put forward here redundant. The aspects covered in this section are simple day-to-day shipboard operational measures that can be undertaken by all ships. In fact, some of them could be implemented also by harbour and port support vessels. During the ship's port operations and at berth, auxiliary engines are run in order to generate electricity for supply to shipboard systems as well as to the cargo loading or unloading machinery where applicable. Today, This power is generally provided by auxiliary engines that emit carbon dioxide and air pollutants. These affect local air quality and ultimately the health of both port workers and nearby residents. As an alternative to onboard power generation, vessels can be hooked up to an onshore power supply that is connected to the local electricity grid. In this way, a ship's operations can proceed uninterrupted while eliminating negative side effects. The amount of power generated and fuel consumed is dependent on the type of ship and could be anything from a few hundred kilowatt to several megawatt of electric power. The operation of auxiliary engines is a major source of SOx, NOx, and particulate matters emissions to ports. The amount of emissions is generally proportional to the amount of fuel used. The longer the ship stays at berth or at anchor, the higher the ship fuel consumption will be, and therefore the greater the exhaust pollutants emitted. Concern over air quality in ports has led to growing pressure on port operators to reduce exhaust emissions, in particular the pollutants of SOx, NOx, and PM. The supply of power from onshore or port to ship is one system that has been advocated for this purpose. The use of this system allows ships to turn off the auxiliary engines when in port and plug into a shoreside electricity supply. As a result, not only are air emissions to port reduced, but it also helps with other aspects of the ship and port operations. It has been claimed that this system, in addition to the environmental and social benefits, could provide economic savings to all stakeholders. This last point has yet to be validated. Onshore Power Supply, OPS, as defined above, has been known for a long time, in particular for naval ships, where the ship normally stays at berth for a long period of time. Under such conditions, it is cost-effective to run the vessel via supply of electricity from the shore. This process was used by the US Navy originally, and the term cold ironing originates from this naval application. Over the years, other terms have also been used for OPS. These include alternative maritime power, or AMP, shoreside electricity, shore power. In the next few slides, the term onshore power supply, or OPS, will be used throughout. The diagram shows a typical OPS system. Ships normally use some base load electricity levels for essential services all the time, including while at berth. For a case of a typical mid-sized tanker, this could be about 400 kilowatts. That excludes the electricity needed for cargo operations and ballast operations. For such a tanker, staying at port for 30 hours, it would require 12 megawatts of electricity. The longer the vessel stays at berth, the larger this figure will be. For an average cruise ship, the electrical requirement could be about 8 megawatts. For such a cruise vessel, staying at berth for 12 hours will require 96 megawatts of electric power. Generating this power on board generates NOx, SOx, PM, and CO2 emissions that could be significant if the number of ships at berth and or their duration of stay or number of calls increases. The environmental profile of electricity generated by power plants on land versus ships' diesel-electric generators that run on bunker fuels is one of the main advantages of OPS technology. In land-based power plants, electricity can be generated at high energy efficiency in large efficient power plants with the use of either clean fuel or exhaust gas cleaning systems. Also, electricity is generally generated in remote areas beyond population centers with minimal air quality impact on population centers. By contrast, shipboard generation is not as energy efficient as land-based plants. And also, any exhaust emissions from engines directly pollute the port and surrounding areas. The reason that shipboard generation is less efficient is due to smaller engines used with an MCR of up to 2,000 kilowatt, as well as port load operations. Engine load factors at berth barely go beyond 50% for most of the time. Installing new shore power systems requires shoreside infrastructure and can be expensive. However, it can also result in major reductions in port emissions. The infrastructure is typically constituted of the following: power connection to utility, power transformation, conditioning and switching equipment, land for these facilities, cabling, synchronization equipment, and berth-side infrastructure. Shipside infrastructure is also expensive, but the cost has been declining with more streamlined and standardized designs. The cost differences between the grid power, especially the high demand charges, and the price of bunker are key factors in the business case for OPS. The low price differential of electricity over HFO can provide a strong incentive to the use of shore power. To use OPS, there will be a need for extra investment both at shoreside and shipside. As the responsibility for supply of electricity to ship is with the port, the capital investment of ports will be more significant. Additional investments stem from construction and installation of electricity supply, conditioning and safety systems at the quay, and potential needs related to strengthening the port's electricity grid. Accordingly, the shoreside system requires the following. Note that the diagram illustrates the typical shoreside requirements. These are a transformer for voltage reduction. The transformer steps down the power supply from a voltage level optimized for distribution, for example 20 kilowatts, to one of the two voltage levels required by the ship. Switchgear for electrical safety. This is a safety feature and requirement. In essence, the switchgear interrupts the power supply and ensures that there is absolutely no power in the cables when connection gears are handled and connection takes place. Frequency converter. The majority of ships operate with a 60 HZ supply, whereas local power grids in many parts of the world use 50 HZ. As a result, most shore-based power connections will require a frequency conversion. Automation system. To allow personnel to coordinate the connection of cables and synchronize the ship's electrical load to the shoreside supply. In order for OPS to become widespread among ports and ship owners, the nature and arrangement of power connections must be standardized. Neither a port owner nor a ship owner can justify investment in expensive equipment to enable a shore connection system without some assurances. They need to be assured that such a system will be functional across many countries with different electrical characteristics in terms of voltage, frequency, and other aspects. Work on a common standard for OPS for ships at berth began early in 2005. Major players in this effort have included technology suppliers, governments, port authorities, ship owners, particularly cruise line, tanker, and container ship companies, classification societies, and others. The IEC, ISO, and IEE have joined forces and developed the international standard that is described on the slide. This standard revised the IEC PAS 60092-510 of 2009 electrical installations in ships, special features high voltage shore connection systems, and addresses the connection between ship and shore and the procedures for safe operation. Currently, and at the time of writing this document, there is no IMO regulation on OPS. In fact, IMO has developed minimal regulations on port development and operation other than those that may directly be required for ships' operation, such as reception facilities. Thus, there have been proposals to add some new regulations to MARPOL Annex Vi on introducing some ship requirements for the future wider use of OPS. For example, it is proposed that ships should undertake an assessment of the environmental benefits as well as cost benefit of addressing emissions from ships at berth. As part of this, it should be taken into account how the supplied electrical power is generated and if similar environmental benefits could be achieved by other more cost-effective means. As part of the proposed draft regulations submitted by Sweden to MEPC 55 in 2006, the following is suggested. Ships that can document that their onboard power production has lower total emissions than the supplied shoreside electricity should, if no other local circumstances dictate otherwise, be exempted from the requirement to connect to shoreside electrical power. No ship should be required to connect to OPS when the planned port stay at the actual berth is less than a couple of hours. The port or terminal should provide sufficient electrical power to sustain all normal operations during the port call, including calculated peak consumption. The cost for the ship to connect to shore power at berth should not exceed the average comparable costs of port services in general and the cost of supplied electricity to shore-based consumers within the vicinity of the port or terminal. There is no doubt that OPS leads to significant reduction in air pollutants in ports and areas in their vicinity. However, the case for overall energy efficiency of OPS, in terms of power used, while including all the transmission losses and overall CO emissions to atmosphere, is not clear. Although both have been advocated by OPS enthusiasts as justification for OPS and reduction of a ship owner's energy costs, this topic is not certain and most likely will vary from case to case. The energy efficiency of OPS relative to shipboard generation needs to take into account all the various forms of energy transfer and transformation losses along the transfer route. In addition, the thermal efficiency of a land-based power plant versus shipboard systems needs to be taken into account. Apart from onshore power supply, or OPS, that can lead to improved air quality in port areas and the likely reduction of greenhouse gas emissions, various ports are promoting green initiatives that aim to reduce air emissions from ships. Green port initiatives are in place in particular in the USA, in Europe, and to some extent Asia. In the majority of cases, reduction of air pollution and improving the port area air quality are at the core of the green port initiatives. Green port initiatives can take many forms and shapes, but the main purpose, as indicated, is to reduce port area emissions. Example activities can include reduce port dues for clean ships, investment in port infrastructure to improve port operations, the provision of OPS facilities, the reduction or exemption from taxation for clean ships. This is the end of the current module. Thank you.